From hammer habitats to tethered designs, today we explore the ingenious ways to bring some gravitas to the final frontier. Over the last few months, we've been deep diving into various types of rotating space habitats designed to provide spin gravity to their occupants, ideally allowing families, communities, and even entire ecosystems to dwell in space. Since we recently explored how centrifugal force simulates gravity, we won't repeat that here. However, today's habitat design closely resembles the classic human centrifuges used to acclimate pilots and astronauts to high G-forces. These centrifuges are designed for one person at a time, whereas hammer habitats aim to achieve something similar on a larger scale. Space habitats like the O'Neill Cylinder, Von Braun Wheel, Stanford Torus, and Bernal Sphere all aim to provide spin gravity for large populations and expansive areas. In contrast, tethered habitats and hammer habitats are about achieving the minimum structural requirements to provide gravity for a crew or a living space. As we will see today, these designs can scale to very large structures and offer practical modularity, potentially making them the most common type of space habitat, particularly aboard spacecraft or mobile facilities. But why focus on these designs? We don't yet know the limits of human or ecological tolerance for gravity variance and rotation rates. However, we have reason to believe that 2 rotations per minute, RPM, is probably acceptable, though 1 RPM is often preferred as a safety margin. Speeds beyond this can become uncomfortable. To illustrate, you can test your tolerance by sitting on a swivel chair and rotating steadily at a rate of about 1 rotation every 6 seconds. 10 RPM. While some people might tolerate this, others may feel discomfort, and prolonged exposure, such as living in such conditions for months, would likely exacerbate these effects. Medications might help, but are not an ideal solution for long-term habitation. If we translate these spin rates into dimensions of spin gravity habitats simulating Earth gravity, the diameter of the ring or cylinder becomes a critical factor. At 1 RPM, the required diameter is approximately 1,789 meters, or 5,870 feet, just over a mile. At 2 RPM, it decreases to 447 meters, or 1,466 feet, a bit over a quarter mile. At 10 RPM, it shrinks dramatically to 17.9 meters, or 59 feet, a hundredth the size of the 1 RPM habitat. For a given level of gravity, the radius, diameter, and circumference of a rotating habitat are all inversely proportional to the square of the rotational rate. This means that having the rotation rate requires a structure 4 times larger. Reducing it to a tenth demands a structure 10 squared or 100 times the size. Each of these scenarios requires significant structural material, particularly for long-duration missions like trips to Mars or asteroid expeditions, where you need a lot of radiation shielding. Providing gravity to maintain crew health during such voyages remains a critical challenge. If it turns out that 1 RPM is the minimum tolerable rotation rate for both the crew and any biological organisms or ecosystems they bring on board, then we must build accordingly. One option is to construct a wide ring over a mile in diameter and 3.5 miles in circumference, roughly 6 kilometers of tunnel lined with radiation shielding, presumably wide enough for crew compartments. Such a structure would be enormously expensive. We won't bother to estimate the cost in today's dollars, as it's hard to imagine anyone requesting, let alone approving, such an expenditure. A more practical alternative is to use a tethered system. In this setup, a pod is connected to the spaceship by a strong tether and reeled out to provide the necessary radius for spin gravity. This tether could be made from advanced materials like graphene superlaminate, which is strong enough to support space elevators. Even a cord thinner than yarn could hold hundreds of tons of habitat suspended in normal gravity. In this case, the pod is essentially a spinning module connected to the main body of the ship, which probably spins at the same rate but far lower spin gravity, allowing the crew to experience artificial gravity without requiring a massive structural ring. To enhance safety and functionality, the walls and floors of the module could be filled with compressed gas, serving 3 purposes: air reserves, to provide breathable air for the crew, radiation shielding, to protect against cosmic rays and solar radiation, emergency propellant. If the tether snaps, the compressed gas can act as a quick propellant to slow the module to a relative stop with the ship. Water reservoirs might also serve in these roles. While compressed gas isn't the most efficient propellant, it could be sufficient for the relative speeds involved. For 1 RPM and 2 RPM habitats, these speeds are approximately 94 and 47 meters per second, or 209 and 105 miles per hour, respectively. The ship would certainly carry enough spare fuel and Delta V to rendezvous with a module that broke free, given the vastly greater amounts of fuel required for interplanetary travel and maneuvers upon arrival. The primary safety system would involve multiple tethers to reduce the risk of detachment. Additionally, both the ship and the module could be equipped with grappling mechanisms that automatically deploy and magnetically latch onto the other, allowing for easy reattachment and retrieval. Another potential feature is a thin-walled, pressurized sleeve connecting the module and the main ship. This sleeve could telescope outward, enabling crew members to drift or climb between the two without requiring a spacesuit. A retractable system like this would also allow the module to be reeled back in, offering flexibility in its usage. For example, the crew could sleep in the module while it's deployed at full gravity. You might have them doing daily operations in zero gravity, or having a command module at, say, half gravity reeled out half as far. If you need more modules, the cost rises linearly, because you just add another module and another tether. Double your space, double your cost. During planetary maneuvers, the module would be reeled in tightly, locked in place, and secured before proceeding. Ideally, the main ship should be significantly more massive than the modules. Otherwise, reeling in the modules could cause the main ship to spin faster, similar to how an ice skater adjusts their spin speed by extending or pulling in their arms. Although maybe you want that, as the spinning halves could serve as a sort of flywheel battery. Slowing them down as they winch in recharges your capacitors just in time for you to light your engines, or before a battle. Tethered habitats offer a remarkably scalable and modular approach to creating spin gravity. Unlike rigid structures, which demand significant upfront investment in materials and construction, tethered modules can be added or removed as needed, offering flexibility for different mission profiles. This adaptability is crucial for interplanetary missions, where crew size, mission objectives, and payload requirements can vary significantly. You might have a single bedroom-sized module or several interconnected ones. If desired, an entire ring of such modules could be deployed, with airlocks between them to allow people to move freely from one to another. Now imagine an interplanetary ferry, similar to the Aldrin Cycler we often discuss. In this concept, a primary spaceship serves as a central hub, with a smaller spacecraft latching onto it via tethers. These tethers could supply communications, electricity, air, water, and even refueling, all while spinning to generate artificial gravity. Entire constellations of small personal spacecraft could attach themselves to a larger vessel, forming a mobile, interconnected community. Similarly, a large space hub could function as the downtown of a space-based community. Individuals or families might tether their personal dwellings to this hub, receiving gravity and utilities like power and water, not unlike a space-age recreational vehicle camp or park in some ways. If they decide to move, assuming their dwelling isn't a spaceship, they could hire a tug to transport them to another hub that better suits their needs or preferences. One could also imagine a sort of support vessel, the sole purpose of which is to be the hub by deploying trusses or cables. This could even store additional fuel, supplies, or cargo at its center, or maybe an even smaller skiff-like drone that deploys from your vessel to link up to another. Or, why not, even no hub at all, just two smaller vessels linking cables to each other's bows to rotate around an empty axis, like a bolus in this Bolar habitat or Bolar Hab. These ships are unlikely to undergo any sort of thrust stronger than what an ion drive could provide. This is meant for the long cruise to your destination, so you could get pretty creative with the combinations. We also have a stronger variation of the tether concept, the hammer habitat. This design assumes a larger module connected by something more rigid, resembling a shaft rather than a flexible tether, hence the name. A more accurate term might be twin hammer habitat, since these are typically built in pairs, and like the Bolar Hab, does not necessarily need a hub. Building habitats in space requires engineering on an incredible scale, and science can open doors to make such insane engineering feats possible. What if the limits of engineering, and even science itself, are not infinite? In this month's exclusive episode, The End of Science, we explore what happens when humanity approaches the ultimate limits of knowledge. Could there come a time when every question has been answered, when every fundamental discovery has been made? If so, what does that mean for the future of civilization, and even for those building new worlds in space? Watch The End of Science, available now exclusively on Nebula. Nebula is the largest creator-owned streaming platform, where every SFIA episode airs early and ad-free, alongside exclusive content from myself and many other creators, including Real Engineering, Joe Scott, and the Science Asylum. Check out other videos looking at amazing feats of engineering, like the insane engineering of the F-14 Tomcat. Sign up at go.nebula.tv/IsaacArthur using my code IsaacArthur to get 40% off an annual plan, $3 a month. Nebula also offers lifetime memberships and gift options, so you can share great content like The End of Science with friends and family. And for new Nebula subscribers, you can get access to guest passes. Share your passion for Nebula with friends and family. With them, they can get free easy access to all Nebula content for a whole week. So go subscribe to Nebula and give a week of exclusive content with guest passes using the link below to get 40% off the annual plan. And now, let's get back to designing new worlds. While you could construct 3 or 4 such modules, at a certain point, the configuration starts to resemble a ring. In fact, you could keep adding hammerhead modules until they form a complete ring. Or several. These modules could also be removable, similar to the tethered concept, allowing people to attach their habitats to open spaces or a central structure. If we think of this design as an analogy to an apartment complex or housing development, the ring could act as a central corridor with the individual hammer habitat modules branching off from it. However, I tend to imagine hammer habitats as smaller systems, intended for stations housing a few hundred people or less. These setups could still be retractable, but likely in a set-up-the-tent way, where the components are packed for transport and then manually assembled at the destination, rather than a simple push-the-button deployment. Why only a few hundred people? The size limit is not entirely arbitrary. While we often assume space development will heavily rely on robotics, there is a practical limit to how much autonomy and decision-making we want to delegate to machines. Human oversight is likely to remain critical. Human-machine teaming generally produces better results than either working alone, unless of course we allow ourselves to be replaced by smarter-than-human AI. That scenario is unlikely, as creating AI with human-level intelligence would erode humanity's unique niche, and with billions of intelligent humans already available, it's doubtful anyone would advocate for such a policy, though there's always a Skynet scenario. Humans need a purpose anyway, so you might as well use them to get stuff done, not just robots. Humans need more than purpose to thrive though, they also need a community. Even for those who are comfortable with extended solitude, such as myself, there is a limit. I can go several days without human interaction, but I still get stir-crazy. Space missions go a lot longer than that. While I once lived alone and enjoyed it at the time, I would not recommend it to anyone nowadays, especially for long-term arrangements. Even for people with active social lives or workplaces, living alone, in my opinion, is not optimal. We can certainly imagine spaceships and remote stations with a lone hermit aboard. While I may think such isolation is unhealthy, there will always be individuals who disagree and choose to live that way, and probably lots of opportunities for them to do so. Our interest lies not just in how small habitats might be, but also in how large. Many operations, however, would have little need to support more than a few hundred people. This number is roughly double Dunbar's number, a theoretical limit to the number of stable social relationships one person can maintain, typically cited as about 150 to 160. This population size also aligns with many historic communities that functioned effectively on a social and practical level. With a few hundred people, you'd have room for multiple social circles, a larger dating pool, children with peers their age, enough participants for sports teams, and sufficient diversity for specialized roles such as doctors, lawyers, and engineers. In highly automated environments, such as asteroid mines, where few workers are needed and additional personnel might be counterproductive, a community of this size might be ideal. In fact, in many cases, we'd likely see much smaller habitats. Though I would not be surprised if laws, regulations, incentives, or even habitat insurance premiums required minimum populations and result in a lot of additional local cottage industry to keep those folks employed. While most of humanity may eventually reside in larger habitats or on planets, the majority of individual habitats will almost certainly be smaller ones, much like the countless minor planets and asteroids in our solar system, which together don't add up to the mass of a single major planet. All the planets combined, both major and minor, still fall short of matching Jupiter's immense mass. Habitats might work out the same. One big cylinder habitat has 1 million people, and its nearest neighbors are a few hundred smaller hammer habitats with a few hundred people each, amounting to just 1% of that cylinder's population. How small can they be? The size of a habitat depends largely on how affordable it is to construct relative to the available resources and technology. In an advanced, post-scarcity civilization, we could imagine a scenario where every individual has their own O'Neill cylinder, fully built and maintained by automated systems. If we consider something more aligned with modern expectations of living space and use a 1 RPM ring habitat, it would have a radius of 894 meters and a circumference of 5,615 meters. Dividing that ring into segments for 300 people would give each person approximately 18.7 meters, 61 feet of ring length. This segment could be as wide and deep as desired. For example, if the width matched the length and included multiple levels, it might provide around 1,000 square meters, 10,000 square feet, per person, not per household. Such a design would still be modest for a Stanford torus. However, for a smaller scale application, like a crew of 30 workers at an asteroid mine, this would be vastly excessive. In that case, you need only 10% of the space in the previous example, or far less since the prior example was quite lavish, and making the ring narrower does not solve the problem. Ring habitats already come with significant mass penalties compared to cylinder habitats for the same living area, and reducing the size would only exacerbate this problem. Instead, a hammer habitat would be far more practical. If your community or company later decides more space is necessary, they can simply send additional modules with tethers or shafts that can be unpacked and connected. Beyond that, you're not limited to a single rotation ring. You could add additional axes of rotation, creating multiple rings as the habitat grows to meet demand. You can also expand an individual module by attaching smaller additions to any of its 4 sides, or even above and below it. This might shift the design from the hammer-like appearance to more of a wedge-shaped module, creating a configuration that resembles pie slices rather than twirling hammers. The upper areas, being under lower gravity, would add weight but could be highly practical, especially for storing bulky equipment. A little gravity often makes maintenance and operation easier compared to zero gravity. For instance, your ground transports for Mars might be stored in a bay above the living area, where the lower gravity facilitates easier maintenance. Zero gravity, on the other hand, complicates tasks like changing the oil or performing other mechanical work. This approach balances functionality with a practicality in design. It also gives you some place to get used to lower gravity during the trip. Needless to say, if you are contemplating more confined spaces per person or smaller crews, like a trip to Mars the next couple of decades, the hammer hab or tethered habitat module approach works even better. This concept isn't limited to living modules. You can also have dedicated agricultural modules that are mostly automated and therefore do not require the extensive shielding needed for human-centric habitats. Additionally, this approach mitigates many safety concerns. A compromised module is far less catastrophic than a breach in the side of an O'Neill cylinder habitat. If you have a smaller space station that needs more dangerous areas like manufacturing or chemical fuel synthesis, or a custom section for visitors to process through, it makes isolation easier. It also opens the door to modules built and launched from Earth initially, then bigger and more standardized ones made at specialized production facilities in space and shipped out to places needing more space. I tend to think that in the longer term, people will prefer more personal space, so the thresholds for switching to larger structures like rings or cylinders might be much lower as populations grow. However, for now, those limits remain much tighter. In the near term, we already know that a well-selected crew can live together on the ISS for extended periods. Depending on the number of astronauts aboard, the available space per person ranges from as little as 50 cubic meters to as much as 130 cubic meters. On a trip to Mars, it's reasonable to assume that providing extra space would be a priority to help maintain sanity. Additionally, while food and water will be packed, having some green space for growing fresh vegetables would offer multiple benefits, including recycling carbon dioxide, purifying air, and cleaning water. Even a crew of 6 likely needs only around 1,000 cubic meters of living space, which is the equivalent to a 10 by 10 by 10 meter cube, or about 33 feet per side. However, not all parts of the ship need to be under gravity. Instead, let's consider a setup with 2 crew modules, one for men and one for women. From a practical standpoint, astronauts are typically married to people not on the mission. While science fiction often envisions married couples on space journeys, this is not a preferred approach in current mission planning. See Robert Heinlein's classic novel, A Stranger in a Strange Land, for some of the reasoning for and against. For now, let's use the idea of 2 modules as a convenient way to divide living spaces. These modules should be designed so that all the crew members could fit into one if there's a problem or temporary shutdown for maintenance. Rather than a simple 10 meter wide cube, we will imagine hammerhead-shaped modules, each 10 meters long, 5 meters wide, and 5 meters deep, or about 32 by 16 by 16 feet, excluding exterior walls. These modules could be split into 2 levels. The lower level might house small bedrooms for each crew member, a bathroom with normal plumbing, and storage. The upper level could be a shared common space with a gym, kitchenette, laundry facilities, and hydroponic equipment. You might have shared facilities between the 2 modules, but having backups is always useful. Plus, you could take one set down to the planet while leaving the other for the crew that remained on board. While it's good for the crew to eat together, they could alternate meals between the 2 modules, and the non-rotating main section of the ship is easily accessible as well. Each hammerhead module might be connected to the ship by 6 tethers, arranged in a hexagon, which could also support a pressurized sleeve around it. This sleeve could even be illuminated and used for growing vining plants. It probably wouldn't be wide enough for a staircase, but could include a ladder and an electric winch or pulley system to move people or cargo with less effort. For a mission like this, the tether or shaft length likely doesn't need to exceed 20 to 30 meters. This setup would result in a rotation rate around 5 to 6 RPM to give you something between 0.5 to 1 full G, which should be tolerable for most crew members, especially with pre-screening for motion sickness and a supply of Dramamine on hand. Full gravity might not be desirable in all cases too. You may want to accommodate them to lower gravity than Earth's while en route to Mars, and might begin at full gravity and lower it towards Martian levels during the long trip, and the reverse on the way home to get them used to full gravity again. This also scales up well if you want bigger modules for a bigger crew of a dozen or more, which I tend to favor over a skeleton crew approach given mission durations. Needless to say, it would help if we could experiment on a space station in orbit of Earth first, to see what minimum radius was needed, though we can always go for a simple tether arrangement and a much greater length if lower RPM is needed. The additional structure required for a hammer habitat's shaft is not trivial, especially if we're aiming for something like an elevator shaft or a spiral staircase. If you need that longer length, you might make a ship with a habitat section and a cargo section that just slipped apart into a bolo hab for the mission, to avoid needing to move between modules much. On the other hand, a spaceship planning to spend several years traveling to and from Mars, possibly orbiting it for an extended period, providing both artificial gravity and an easy way to move between modules would be highly beneficial. Hammer habitats could also prove very valuable in low-gravity environments like Mars or the Moon. By combining spin gravity with local gravity, you could tilt the floor inside the module diagonally. The lower the local gravity, the more the floor tilts toward the vertical and vice versa. Entire habitats could be designed at this angle, spinning to create artificial gravity. These configurations, often referred to as bull habs or rotohabs, tend to be deeper than they are wide. We don't yet know how much gravity people on Mars or the Moon will need to remain healthy. It is possible that the minimal gravity of these bodies is sufficient, which would make building rotating habitat sections on spaceships much simpler. However, if it turns out that additional gravity is necessary, the hammer habitat approach is a practical solution. For instance, you could build a tower on a low-gravity body and swing modules around it, or even land a spaceship equipped with pre-existing hammer habitats. In low-gravity environments, a tethered swing from a tower would not trace a perfectly circular path, but instead follow a shape resembling an umbrella. This would require a taller tower. Alternatively, you could keep that path flat and use a more robust central shaft for the module to rotate around. It wouldn't take too much power to keep that spin going, even in the thin Martian atmosphere, but the more radius you needed or lower RPM, the faster that habitation module is spinning, and the frictional losses will rise sharply. But it should be quite viable at the same scale we were discussing for the ship traveling there a moment ago. Where the gravity is the same as Mars but there's no atmosphere to cause drag, you might construct a large umbrella-like structure over your base to collect solar power and reflect excess sunlight. Around its edges, you could run a hammer habitat to provide full gravity for the crew, allowing them to spend most of their time there while mining or farming is conducted in the lower gravity of the central base. Fundamentally, where gravity is needed but population or infrastructure requirements are low, the tethered habitat or hammer habitat approach will likely be the easiest and most practical solution. For quite some time, these designs are likely to remain the primary way we generate spin gravity for crews in space. Later, as our presence in space grows, we can build larger ring habitats and cylinders. However, even then, it's likely there will still be far more tethered and hammer habitats than rings or cylinders. While the latter might house larger populations and provide significantly more total land area, they represent a major investment in resources and construction. They won't be necessary until we have far more people living and working in space. This is where hammer habitats play a crucial role as the first step toward a future filled with larger megastructures.